Okay, folks, now we're going to play the same game that we just did with the solid liquid boundary. This time, we're going to look at the liquid vapor boundary. And some things will change just from that difference in looking at the liquid over the vapor versus the liquid over the solid. Okay? So here we can see a typical boundary for liquid vapor, and it's not nearly as steep of a phase boundary as is the solid liquid. So we still will apply the Clapeyron equation, dP over dt. And this time now we're considering that this is vaporization. So that's delta H of vape divided by T times delta V of vape. Okay. So now in considering this delta V of vaporization, that's going to equal the molar volume of the gas minus the molar volume of the liquid. And because the molar volume of a gas is just so much larger than the molar volume of a liquid, we can effectively ignore that molar volume of the liquid and say that the molar volume of vaporization is just effectively equal to the molar volume of a gas. And so I'll give you an example of that. If I look at like a typical liquid density, 1 gram per milliliter, okay? So if I go through that for liquid water, let's say, so that becomes the same thing as 55 moles per liter. So all I did was turn a gram into mole and a milliliter to a liter using water's molar mass. But now remember, that's the density. I want to flip that, right, to express that as a molar volume. So flipping that, 1 over that becomes 0.018 liters over moles, which is tiny, right? So that's the value for the molar volume of a liquid. So we know a good value for the molar volume of a gas, at STP is 22.42 liters per mole. So again, we can see the molar volume of a gas is enormous compared to the molar volume of a liquid. So we won't worry about the molar volume of the liquid in this calculation. Okay? And so now that means going back to my Clapeyron equation, dP by dt is still going to be delta H of vape over T. But now for delta V of vape, we're going to plug the ideal gas equation in. So instead of saying Vm, we remember that Vm for an ideal gas is RT over P. So we're going to plug RT over P into that part of the equation. And now we've got to go through the same game that we played before by separating our derivatives and integrating both sides. So cleaning up our algebra a little bit, this becomes delta H of vape. I've got a 1 over 1 over pressure, so now pressure is in the top. And then now we can see that there is a T squared and an R. Okay? So now going and separating these things, I actually have a P to keep with the P and a T to keep with the T. So we'll note that that is now dP over P. And I'll move the dt over to this side. That becomes delta H of vape divided by R times dt over T squared. And now we do the exact same thing, right? We'll integrate both sides from condition 1 to condition 2. And then recognizing delta H of vape over R, we'll treat as a constant. So we only need to integrate dt over T squared from condition 1 to condition 2. And then we get the following. So this integral becomes the natural log of P2 over P1. And all of that equals the following. So when we integrate this thing, dt over T squared, we're going to get a negative delta H of vape over R. And that becomes 1 over T2 minus 1 over T1. And I'm going to continue this along on the next slide. Okay, so continue along. I planned that well. Sometimes I don't always plan my slide craft very well. Okay, so let's rewrite what we came up with. 1 over T2 minus 1 over T1. And so I'll remind you that this is the same thing that we did before, where like if I look at some arbitrary point here, I could describe that as so P2 and, I got a phone call that you might have noticed and now it distracted me. Okay, so that would be P1 and T1, right? And some other point up here will be P2 and T2. So typically then we would use other reference values. Okay, so I'll keep going on with the algebra here and I'll describe what our reference values will be. So I'm going to take E of both sides, and that gives me P2 over P1 equals the exponential of negative delta H of vape over R, 1 over T2 minus 1 over T1. And then I'll do one more algebraic step, and we'll say P2 equals P1 times the exponential of negative delta H of vape over R times 1 over T2 minus 1 over T1. And this, you might have remembered this from Chem 109, perhaps, is the Clausius-Clapeyron equation. So we remember the Clausius inequality from before. The Clapeyron equation is what described the phase boundary. So now we have the Clausius-Clapeyron equation here. And so what I want to point out, it's typical to take P1 as atmospheric pressure. So we'll say PATM, which means then T1 is what I'll call the normal boiling point. And if you recall here, with respect to the liquid vapor boundary, right? If I've got a container here with some liquid in it, right? When the vapor pressure of that liquid is equal to the pressure of the atmosphere, the liquid is boiling. So that's what our T1 and P1 corresponds to, right? So P1, would be atmospheric pressure, and then notice now the way this equation goes, we could use any units we want because of the ratio of the pressures. Temperature still has to be in Kelvin, of course. And now T1 is our boiling point at whatever atmospheric pressure is. So what I'll also point out is not only does this describe our liquid vapor boundary, but this line right here gives us vapor pressures of our liquid at any temperature. And of course, when that vapor pressure is equal to atmospheric pressure, the liquid is boiling. So if I look at this on a graph, I'll just kind of draw separately right here. Like here would be my vapor pressures and here would be my temperatures. If let's say atmospheric pressure is way up here, PATM, right? You can see there's an exponential increase in this curve, right? So anything along this line would just be the liquid in equilibrium with its vapor, or in other words, my vapor pressures. As soon as I hit atmospheric pressure, that would correspond to my normal boiling point, okay? But certainly if I could pump vacuum over my liquid, right? Let's say I pump this thing down, then I could boil this liquid without heating it, right? Which makes good sense because boiling is related to the liquid's ability to elevate into the gas phase. And if the pressure above the liquid is reduced, it's going to take less energy to put it up into the gas phase. Okay, and then now one last quick detail. What if instead we have the solid vapor line that describes sublimation, right? Well, as it turns out, we can use the same equation, the Clausius-Clapeyron equation, and it just goes as the following. P2 equals P1 times the exponential, and then now instead of delta H of sublimation, instead of delta H of vape, we use delta H of sublimation. So it's the exact same equation. Okay, so that's, let me clean that up a little bit. That says 1, I don't even know what that says myself. Okay, let's fix it. 1 over T2. Okay, beautiful. All right, folks, that's it for this video. One last video in this module. I'll see you then.